have to try to stay still. So, okay. So in this splitting, we draw, say, this equation here bigger. Okay. And say this is a shape at time t, fixed t, this one. And this is just sigma at t plus the t. So again, infinitesimally small shape created from sigma t. Say we fix a point here that we call P, and there is another here Q. Okay, so here what we would like to do is to connect these two that are space-like equivalent. What it means is that if this has a P has coordinate xa t, Q coordinate xa plus the t. Okay. So from this, okay, we see that we can say, okay, now I drew it as a curve. Maybe it's better to do it separately. Because it's small, and we call this quantity, this vector here, t mu. Okay, and this t mu, which of course it's going to be actually the derivative of x mu a x a over the t. So basically, it's just the fact that we have for the whole space-time the coordinates capital X mu, and this corresponds to really just x mu prime minus x mu. Okay, varying only the time parameter. So I want just to write down this. Of course, we can connect by a different formalism x mu and the other coordinates. So say x mu t, and well, just from this we see that. Can you see standard here?
Yes.
Okay. So we'll just say delta x mu over t. This, and of course this leads to just this. Okay, without writing this, the t. Okay. So yeah, that's exactly what I'm doing here. And this also 2 points P and Q in the capital coordinates are just this and this. And so we are evaluating exactly the difference as a vector. And this we can, of course, decompose it into 2 parts. Say this and this. We call n mu the shift vector, which is tangent to this segmental at the point P. And instead, this one here, we call it n mu, and this capital N is called the loss function. It's just kind of a coefficient of the vector, and this little n is the normal vector at a point P. Okay. So it's kind of a parallelogram rule. So we can write it as n. Okay, x say mu xa. Sorry about that. Plus n mu. Okay, and of course there is also t and xa.
May I ask? Maybe I missed something, but why did you choose P and Q to have the same, let's say, space coordinate, sigma coordinate as A?
Why?
Yes, why?
Well, first of all, we would like to know the difference between, I mean, how kind of a space fixed point varies along time. Okay, because if you want to do that, I mean, of course, as I told you, here we want to split this d4x into dt d3x. So we want to split in this new coordinates here, okay, here. So the coordinates from this to this, okay. And well, the point is that we have to also do, say, first of all, to pull back all the tensors defined on the whole space-time to hypersurfaces, first of all. And so we need a relation between the old coordinates and the new coordinates. And well, another reason, there is also, you know, a property of this vector here, which is the fact that, first of all, well, actually there are many properties of this. One property is that, okay, first of all, n mu, little and capital N are orthogonal with respect to the metric G mu union, okay, because in this sense they are orthogonal. Then, okay, and mu is orthonormal, as I said, and also that G mu union and mu is bigger, it's bigger than 0, which means that it's space function. Okay, so in this way we have a good way how to define space-like and time-like tensors, whatever.
Isn't the point just this is a definition of your small coordinates? You start by choosing P and Q, and then you say, well, I'm going to choose small coordinates so that they are on the same coordinate point in the small coordinate. So it's just a definition of small x.
I thought that it was a deeper result.
I mean, that depends what you say first. If you say, okay, I have small coordinates, I have big coordinates, and then I'm choosing P and Q to be in the same coordinate point. That's one possible way of saying it, or you say the other way. I'm having P and Q, I want them to be at the same coordinate.
Yeah, so this is the definition. Okay, good.
Yeah, I guess a purist would probably think it would be nicer to have a geometric starting point. So say we start from a time-like vector field T mu or something like that, and then from a Cauchy surface propagate the coordinate system.
Yeah, sure. I mean, this way you can you just split actually what is space like and time like. Of course, we can do it in many other ways. It is not the only way we can do. But actually, I never thought about this. Maybe it leads to something. It's just a good choice that leads to something very simple at the end of the calculation, and also a nice interpretation at the end. Because also we have here the shift and lapse vector, if we define it like this. And we know that the shift and lapse will be just Lagrangian multipliers, so we have a nice structure of the Hamiltonian and the constraints. It turns out to be useful. Okay, so yeah, from this, we would like also to do another thing that's important. That is how to, starting from the G mu nu tensor, to define a magic tensor not for the whole space-time, but only refer to space-like hypersurfaces. And how can we do that? We need also this quantities here, and we define so Q mu nu in coordinates. And the coordinates of the whole space-time, so the capital one, so the G mu nu plus n mu n mu. Here, these orthonormal vectors, and this is important because if we contract this metric tensor with any say orthogonal vector at a point of that hypersurface, it will be 0. So we have that n mu q mu nu, and we also hold for the other n nu equals 0. Okay, so in this sense, this q mu nu starting from g mu nu is just the metric tensor for the space-like submetrics. Okay, and it comes from the fact that m mu nu and mu nu gives -1 and cancel out with each other. And also we have another property q mu q mu sigma, that is q mu sigma. That's actually not the delta. Okay, this is just delta mu sigma plus n mu n sigma. Okay, but this is not a problem, of course. Then, once we define this new,
Well, I mean, you didn't really say what Q with indices are.
oh yeah, I mean,
So
okay,
you
we have to raise the indices with G mu nu, not of course with itself in this sense. So we have that Q mu nu equals Q mu then we want to find a new covariant derivative, not the nabla, and we want to just to write not for creating confusion. We have two methods.
Please.
You're yeah, I want to find a new metric tensor for this sigma specialized surfacer, and we have to implement three conditions, of course. The compatibility with metric has to be torsionless, and also the speciality of the be spatial of that covariant derivative. From the compatibility, we say that first this condition is d mu q mu rho equals 0. Torsionless to be d mu f equals 0 for any smooth function of m, and also big special. That is that if we I mean the contraction between this orthogonal vector with the covariant derivative of a general vector, so it could be decomposing to normal and also tangential part, has to be 0. This is for any u mu. I mean, just vector on m such that u mu and mu equals 0. So this has to be general. Okay, sorry. This u has to be tangential, so it has to be orthogonal with respect to the geometric to n mu.
So it is a tangent of this sigma.
Yeah, sure. So, and the unique solution is that this d mu on function has to be q mu nabla, mu f for a function. So basically we just raising and downing the instance with the new metric, and that u mu has to be rho mu this way. Yeah, this can be proven just an exercise, satisfies all of this, and that's unique. So once we define this covariant derivative, we see actually that there is another step that we have to do, and the step is that starting from the action, yes, and the action. As I told you before, we would like to write in the new coordinates the g, r, and the measure of the integral. Okay, but of course we have to say that the r that I consider for the four-dimensional space-time has to be somehow related to the three-dimensional plus something else. What is this something else? Well, the point is that we have the sigma surface, just pick one sigma submanifold. That's actually a manifold. I mean, we know that there is an embedding between, from that sigma into M, the total space-time. And when we have this three-dimensional surface, manifold, to be precise, into a 4-1, what happens is that we have to consider also the so-called exterior curvature, or also the second fundamental form. The reason is that when we have submanifold hypersurface of manifold, the exterior curvature, roughly speaking, measures how the orthogonal vector at a point changes if with the other changes, if we parallel transport it along that surface. Okay, for example, if we have this curve here, one-dimensional in as an embedding in the blackboard, and we have here the orthogonal, say n mu, just say n mu, but just the point is that say that here we have instead the orthogonal, here is n mu prime. If we parallel transport these in here, you will get this, okay, this other vector. And the point is that the exterior curvature measures the difference between the two. This n mu prime and say n mu. Okay, so what we are expecting is that in this curvature, it will emerge also the exterior curvature. I'm not going to do all the calculation, but we start from the fact that we call this k mu on m as d mu and nu. It's not a definition. It comes from actually from the mathematics, that is from the Weingarten map, that comes exactly from the orthogonal vector. So as a tangent map at a point x or vector, orthogonal vector. So it comes from that, and we know that it's symmetric tensor that is interchanging mu and nu. It's the same, and yeah, it comes out that in coordinates and with this prescription with n mu is exactly leads to this. Okay, and yeah, but we have to also move from the total space-time to the sigma space. So how can we define this k? How does it transform when we start from m and move into sigma? So want to write on sigma, it has to be with k q mu, sorry, remember. Q mu from sigma. So basically using a new method. And okay, so now I told you there are like 3 pages of calculation, so there is not worth doing all of this. But the final result of all of this is that the relation between the fourth and the three-dimensional spectrum Ricci scale are these. Okay, where K is like defined to be Q mu mu K mu mu. Okay. So we know from this and insert into that action.
So what again? What is R3?
What?
What is R3?
R3 is just the Ricci scalar for the sigma.
Which metric?
With the new metric.
Q.
Yeah. Yes. So
Isn't it just the three-dimensional metric?
mean, there are two possible metrics you could think of for sigma, at least. So the metric, there's Q, but you could also think of just pull back the space-time metric to sigma.
Yeah,
two different metrics.
In fact,
It's
now,
the same.
No, they don't.
No,
Well,
that's
in
not-
that, yeah, of course not same, but maybe they keep the same value.
That's possible. Yeah, that's
Because the point is that the Q is basically zero in the timeline
Mhm.
direction. It's like a projection to the,
Right.
to the.
But I
yeah,
don't know if
then,
they are-
in fact, what we are going to do next is to pull back. And we'll see that exactly coincide with the ones purely on sigma.
What coincides?
I mean, the tensor k mu nu, for example, if we want to pull it back to sigma, it becomes basically KAB, where AB are just in the new coordinates of XA.
Yeah,
Okay.
but what I was thinking, or what Klaus was saying, is that R3 will be the same,
Yeah.
independent of if you
yeah,
calculate
exactly.
with Q
Yes.
or with the pullback metric.
Yes.
But I mean, that's certainly not trivial thing. Intuitively, it could be true, but I don't see it. Calculation of it.
Yeah, I think that's very long. But they coincide again. So at the end of the day, we can write this R3 the same form that we write the rich scalar for the 4-dimensional, but just using the new metric the new metric not only Q nu, but also the metric that I'm going to write right now. No, it's not very simple to explain. Okay, so yeah, what we're going to do is to replace that this in that. For now. Then what we want to do now is to exactly write it in the new coordinates t and xa. So we know that this for x is going to be dt is x, okay, and yeah, this square root of minus g. How does change? We have that g mu can be written as just say g metric is new. Okay, and here we have, of course, from the capital to the small one, we have to differentiate because they are one forms. And so we have the contribution from the derivative of the time and the contribution of the derivative with respect to the spatial coordinates. Okay, so here we have x mu comma t, I write just okay, I erase it. Just the derivative of this mu with respect to t. Okay. T plus x mu comma a. Say, and here.
Yeah, you change it.
Okay. And now we know that d x mu comma t is exactly what we defined above, and I erase it. That is the t mu. Okay. So here we have the contribution of the lapse and shift guys. And what's the meaning of this instead? The meaning of this is that when we contract any answer in the mu space-like indices, it pulls it back. So it becomes exactly a tensor on the sigma hyperspace in the new coordinates. Hopefully it's clear.
Well, it's the definition.
Yeah, well, this is just a change of coordinates. The old into the new ones, of course, because we have the derivative of this with respect to xa, so it's just that. So when we do all of this and substitute weight with what I defined above, and this x, as I told you. Okay, so blah, 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 at the end of the day, it becomes minus. Okay, maybe I need some more space here. Can you see standard?
Yes, it's fine.
Okay.
So where QAB is what?
Yeah, QAD is just okay. So just
Why not G mu?
here.
There,
Why G
because that's what you have there. Your
No, well, yeah, but no. The point is that, as I told you, this G mu nu it equals Q mu nu minus N mu and nu.
yeah,
Okay.
yeah.
So yeah, I just
So what happens with the other part? The N mu stuff.
okay, I'm going to do it. Okay, I just okay, so yeah, the next step is let's choose new. Yes. And that's the same here. Okay. minus this with this becomes you know
I can see those guys, but
Yeah,
let's
the
say
point is
let's concentrate on the last term there, which is QAB, DXA, DXB. So that will come from the G mu nu, this X, yeah, the X mu.
it comes
X.
from this and this.
Right. So how do you get a Q and not a G? Then you have to use something that you haven't spelled out.
Oh well, just because here we have from G mu nu this and this.
Yeah. Okay.
Okay, and now of course this gives QAB, but this of course will be 0 because it's just the pullback onto sigma of a normal vector. Okay, so that n mu x mu comma a equals n a equals 0. That's the point.
Well, I mean, what you're saying is that in the new coordinates,
Yeah.
the metric is diagonal. There's no T X A X A. Isn't that what you're saying?
I want to tell you that it doesn't mean that the contravariant and mu is 0.
Oh no, sorry, it's not the DDT scalar product with DDXA. It is DDXA, but with n.
Yeah, I guess by definition, when you differentiate with respect to A, you are in sigma, a tangent,
Right.
the tangent space with sigma, and n is by definition
Mhm.
perpendicular.
Well, yeah. I mean, not quite yet in the tangent space.
Well, I want to tell you that if we have n mu here and we write it as n t and a, okay, the new coordinates, this n a doesn't have to be 0. Just the covariant and mu here has to be n t 0.
Right, sure.
Okay, so in this case, it's exactly this.
Yeah, but you can understand this in the full space time. I mean, so if you do that, what you're doing, I mean, or this calculation, you're taking n, and you're taking DDX, which is DDXA, which is a vector. You have two vectors, n and DDXA.
Yeah.
And you said it in the beginning that those are orthogonal, that's how you choose it, but you didn't write down the actual equation that would mean, and the actual equation is this, if you use the original metric to say what you mean by orthogonal, to define orthogonal.
Yeah,
And it's this.
it's clear now.
Yeah, I think it's clear. Yeah. So that also would help with the question that we had with Klaus, that actually now when you pull back your metric, you do get Q, the same as when you pull back Q. So then there is no issue what metric you're using when you factor the R3.
That's why this R is the same, has the same form in Q mu nu and QAD.
Yeah, it would be more complicated if you're calculating some tensor, because then you would have to say in which coordinates you're doing it, in the big X coordinates or small X coordinates.
Yeah.
But here if it's the scalar, I think it's
Okay. So. What time is it? Nice. Okay. Yeah, I was very hopeful to do what I tried to do, but actually I did less than the half. So from this G, we can write it in the matrix. We see in the new coordinates as minus n squared. Okay, and here. All right. So in the sense, I mean just as a matrix, not as the determinant. Okay. So the determinant of this turns out to be that when we basically multiply this with this and subtract this and this, what cancel out are exactly these terms here.
that's
Yeah, I know that. Yeah, of course.
not the way to do it.
I know, but it's just a very quick.
No, it's something that you can say when you know the correct result, but you would never.
I know that
You shouldn't use that argument. ever.
that's just 1, 3, 3, and 3 by 3 matrix. I mean, just 1, 3 components, and 3 by 3. So of course we cannot do that, as I told you. It's just it turned out to be that only these terms cancel out. Okay.
But that you cannot claim to see just from.
No, to see from this, yeah, exactly. No. Yeah.
You know, do you know a good way of calculating the determinant of something like this? No.
Is that
No, I mean, I have a good way of doing it. So if you're interested, I can explain to you how I would calculate it.
well, we can use the Laplace, for example, method. Like choose this one and try to do, you know, the components of the minors and so on.
That would be, then you would have to, you know, write out Q1, Q2.
Actually, yeah, that's not the best way. That's how I did it time ago.
But, you know, it's one thing you can do is to write this matrix as a product of two triangular matrices, where there are zeros below or above.
Yes, that's true.
And then you can take the determinant of each of those.
Yeah,
And then you get the determinant of the blocks, which is
that's true.
easier. So you know, it's not a problem to calculate the determinant of this, but you cannot do it the way you suggested. Just look at it and that's it.
Okay, so since we need the determinant, here we have yes, minus the square determinant of QAB. Like this. So yeah, with square root here just gives us to n and the square root of the determinant of q here. Okay, that's in the new coordinates. And the new coordinates, as I said, this doesn't change, and this give.
Yeah. Good. That
Give want to cancel here. So once we, okay, another thing is Q mu K mu has to be K D K B. Okay, and this K just told you that was G Q mu nu K mu nu, and it becomes like this. So just to put back it has the same form.
That's also not completely obvious.
Because no, actually it is because we have that n sigma. You're talking about one, and that we know is perpendicular with respect to the metric. I mean that Q mu nu and nu equals 0.
Yeah.
Okay. So yeah, of course we have. We have also to write the nabla compatible with Q, the new metric, and then we can move the Q inside. And
Yeah, okay.
goes
So you see,
here.
it's a little bit of computation. I mean, what you really should show that in that tensor, when you pull it back, that it has zeros in the appropriate places.
The point is that to prove or to do all this calculation takes a long time, and so I prefer not to do all this and just to say, okay, that's what it turned out to be, because otherwise I cannot do anything. It's
I don't. Well, of course you have to. You can't do all the computations, but the point is where to draw the line. And if you draw the line too early, then I don't think it will be as useful for other people, because it's just going to be like a bedtime story.
Okay, so we can write that as okay, as Q, I just write the determinant of Q. Write it at Q. Okay.
So why is it not square root? Why is it not square root?
Yes.
We ask, is n manifestly positive? Is n manifestly positive? Because we're actually doing square root of square. So shouldn't there be absolute variable?
Actually, no. You mean outside the absolute value or here the absolute value here?
No,
N.
The end. Okay, so plus or minus here. Actually, no.
Just give the definition of them again, the picture, and you'll see why.
So, okay. Well, also another point is that if we have a plus or a minus, it doesn't change anything. Maybe the only thing that could change, yeah, but the signature could change actually.
No, not about the signature. I mean, your N tells you that you're
Direction
propagating
of
forward in
up.
time.
Or in time, yes.
So if N is positive, you're propagating forward. If N is negative, you're going backwards.
Yes, but the action doesn't change. I mean, you get plus or minus, of course, but the equations doesn't change and so on.
Oh, but what if it changes sign and you debate over it? So
Yes.
then it will be probable. I'm asking, okay, so the N basically describes the direction, the arrow of time. Then the physical reason probability is that it doesn't change its direction.
Yes.
Okay,
True.
good, thanks.
And okay, just write down because it's now 3:10. So before, okay, I just want to stop here. Yes. Why is this way? That's quite long, but at least I want to start from this. There's another part of this. We write it here. Q out and Q. So D and yes, square. So what I did here is just to, well, it's not just, but okay, we have the square root of Q and multiplied by this, that's the first part. Then these QAB are related to both the time derivative, say, or time parameter derivative of the metric and the Lie derivative of the metric along the vector field, the shift vector field. And the point is that I ask why. Suppose that we have q mu mu that remind you that we had the definition of q mu mu the covariant derivative of the normal vector and so if we symmetrize, we get the derivative, okay, of the metric.
Again,
Well, we know the lead derivative of the metric tensor.
yeah,
Respect to
but-
vector field is just the symmetrized.
Yeah, you just erased the two definitions, and there were two different cases. Which
Mhm.
case was it? The ordinary covariant derivative or the new covariant derivative?
Yes, that's true. The new covariant derivative of the capital D.
Yeah, so then to believe this, then I would have to believe that the new covariant derivative behaves like the standard covariant derivative, but with respect to Q.
Yes. Yes.
Which you haven't shown. Have you shown it?
No, I think I didn't. But it's just how we define the new covariant derivative.
Yeah, with some projections.
Yeah, that's.
But that doesn't mean make it a covariant, but behave in the same way as the standard covariant derivative can compute it using a connection, which I get from the.
No, but remember that the new covariant derivative capital D for a covariant tensor like the metric is just Q, Q, and nabla.
Yeah.
Okay, and that's what we got also in Q mu nu. That was Q, Q, nabla. So actually, it was capital D.
Right, but does it behave as the standard covariant derivative? Where I have
Not as the previous one.
Well,
Not-
then I'll see that because I know that this is true for the standard covariant. But if I take the nabla vector and symmetrize, I get the
since it's
derivative.
compatible with Q, of course, it gives the same Lie derivative. If you write down the Lie derivative of a tensor in coordinates,
Yeah.
and if that metric, that covariant derivative is compatible with metric, you basically get the covariant derivative of that, say, tensor with respect to the components. And that's exactly.
Well, you haven't shown that it has the properties of the covariant derivative.
If we have that's more, but so that we have T as a PQ tensor.
Yeah, I know what the covariant derivative.
Okay,
I know what the
yeah,
Lie derivative is.
It gives the points that we have in coordinates the partial derivatives of this tensor with respect to some coordinates, if they are up or down, okay? And those partial derivatives can be replaced by a total derivative, okay? Because that's
What do you mean total derivative?
the covariant derivative, because it's compatible and it's torsionless. If the connection is a Levi-Civita connection we have, then we can replace all of those with the covariant derivative. Well, that's a fact, I know, but I mean, you can prove it by calculation, but the point is that if you have, repeat, covariant derivative, say, using the Levi-Civita connection, then all the partial derivatives in this V derivative can be replaced by
No,
new
it's
covariant.
not. It's not only about being compatible with the metric. You
No,
can
it's
do it,
torsion.
you can do it if there's torsion.
It's the Levi-Civita.
Yeah, you only said compatible.
No.
That's not
I said it's Levi-Civita. Has to be.
I don't know if it's true if you have. Okay. Yeah, so, but that's, again, it's not my point. The point is,
That's to say that we can write this in terms of the covariant derivative, the new covariant derivative.
which we don't know if it's the Levi-Civita. You haven't shown it.
Oh, but it is of course Levi-Civita because we started from
Yeah,
G that is
with some
Levi-Civita.
projections. I can start with something, I do some crazy projections, I get some derivative, which doesn't have to be Levi-Civita.
We are in the second order formalism actually. I mean, I started from the Einstein-Hilbert, not from the Pollari.
Yeah. But you define a new operator, and you didn't show that operator, using some projection stuff, you didn't show that operator.
Yeah, sure. Well, the point is that when we define the new covariant derivative of on a tensor, general tensor, then of course we have the partial derivative first, and then we have the connection.
Right.
Okay, and that connection is still symmetric because it's right because the Q mu nu is symmetric.
Yeah.
And so we have only the symmetric part of the connection.
Yeah. Together with some, I mean, there are some projection operators on it.
Pull back me.
Some Qs, yeah, some Qs. You have Qs on the connection.
Yes.
Yeah. What do they do? I mean, can I show that the connection coefficient computed with the original metric, and then I attract some Qs on it, and I get the connection coefficients computed with the Q metric. You know, I believe it's true what you say, but you didn't give me enough information to compute it, to really verify that it's true.
You're right. Well, but you know, we constructed that D from the fact that it has to be torsionless. That's one of the conditions to create the new covariant derivative. There were three. One was compatibility, one was torsionless, and the other was being spatial.
Right, but you didn't prove that those conditions were true.
Okay, but I mean, it was just an exercise to check it out. But I said, I mean, let's just take it because it's.
Again,
I can understand your point of view, but you have to understand my point of view. I cannot do all the calculations. I just said these are the properties. This is torsionless, so it's Levi-Civita.
yeah, but then you could have just started with this. Actually, this is it. Define your stuff to start with. This is what I'm starting. I'm just trying to you know, put in what for me is information that makes what you're saying into something that I can sort of accept. And it's an art to learn what to not say. It's very difficult, but the only way to learn it is if I tell you what I'm missing from what you're
I
talking about.
accept and appreciate it.
So if you say something, then you should say some other things. Sometimes it's better, if you decide not to say B, also not to say A, because A sort of points at something, and you're sitting waiting for B, and B doesn't show up, and then it's strange. So when you started doing some calculations, I'm trying to follow the calculations, but then I'm missing some information. I can't really verify it. I don't see where it came from.
Yeah, because I cut off many of those and just get to the point, and so it's kind of a belief. Say, kind of if you can't see that, I have to show. But
maybe it would have been enough to say, well, so actually if I would do this calculation, I would take this operator, show or try this or something, then I would verify that this is true and go on. Just so that I know sort of where to start, so I can do it in my head.
Yeah, the thing is that there are too many information in all this setup, and truly you need some more than the others, more useful. But the other point is also that if you take any say formula, either you do all the calculation or otherwise it's never clear. It's something that also some people, I have to say that some other people think that this is the way how to see that. For example, let's apply to this case. When we have mu equals that the derivative, I could explain why it's like that. So following all the path from the beginning to the end, like the derivative is defined for in coordinates with this tensor as the partial derivative, and then we use the fact that it reduced to the a total, covariant derivative. If the covariant derivative is Levi-Civita, so that's what I said. It was torsionless and so on and so on. But I just thought
that I completely understand. I have no problem with that. That's stuff which is well known from differential geometry. So if you know differential geometry, it's okay. What I didn't catch was that your new covariant derivative was really a covariant derivative. That part was missing.
to prove,
right, or indicate.
To check out all the three properties that.
Or at least say what calculation you would have to do to check it or something. But this is fine with me. So then you would have to put in the antisymmetric part, I guess, also.
Now, to write like this, and yes, and this, if we want to.
But it's not equal now.
1/2, yes.
It's still not equal. You have an antisymmetric part. What happened to that?
Here.
On the left, K mu is not symmetric.
It is.
How come it's symmetric?
We said that, the K mu, I give the formula.
Yeah, it didn't look symmetric to me. It looked like covariant derivative on n, not symmetrized.
was like this.
Yeah.
Something.
Yeah, this is not symmetric.
Actually, it is because if you substitute this q mu rho with the delta plus n mu and rho,
Yeah.
okay, let's do it. Okay. Yes. Yeah.
Let's see.
Right. Then
The last term, there should be an n new, not the same. No. And, oh no, there are two. Oh, sorry, you're right. Yeah, I was looking at it.
okay. All right.
Yeah, why is this symmetric? The first term doesn't look symmetric at all.
Well, what I'm thinking is to from this part. Just a second. I'm thinking here. To write it like this,
Okay.
and this is -1.
Yeah. Fine.
This is again -1.
Okay.
So this that's the same stuff actually. So it's much simple. Okay, wait. As I showed that with the QQ and the old nabla gives the mu, and so it just half of summarization. Sorry, not this plus. Okay,
Plus a half d mu nu minus
minus the other part of the symmetric part.
This is the symmetric part plus the antisymmetric part.
Exactly.
After the antisymmetric.
The antisymmetric part. Okay, now this is exactly that, right? And this vanishes because, as I told you, it's torsionless. What is that?
Nothing to do with torsion.
It's not the commutator.
You know, the
Oh, yeah, that's true, that's true.
It's just the covariant derivative,
Mm,
not the
wait,
no, it's not the it's just the partial derivative.
the partial derivative.
The coefficient, connection coefficient vanishes, but the partial derivative doesn't.
Yes, that's true. I cannot see.
Are there no antisymmetric terms? I thought that would be part of what you're writing on there, some antisymmetric stuff. But maybe there are not, I don't know.
So that this is mu and nu should be symmetrized.
Sorry?
So that the mu and nu indices should be symmetrized.
No, I was thinking, you know, the K knew that there would be two terms because I can see when he was writing, there are some terms with Lie derivatives in them, but there are also terms with no Lie derivatives. So if I take my K A B and I just put in Lie derivative stuff, then I just get Lie derivatives. So I was thinking, you know, maybe there is some antisymmetric part which can be written as, I don't know, time derivative of Q or something. I don't know. And that would contribute with the other stuff. You know, where does the Lie derivative and the time derivative of Q stuff come from? That would seem like a cross term from one of these things. Q is symmetric, yeah, so I don't know how that would work, but somehow from that. So cross term would work, symmetric and symmetric, that's true. So that will now, yeah, you're right, you're right. Yeah, I don't know.
Is the electrosymmetric part equal to 0? But like the surface also covalent, or at least the partial derivative part of it.
The antisymmetric part
is orthogonal to a hypersurface, and its rotation is equal to 0.
Yeah, that gives the Gauss close retention.
Does it have to do something?
Liberals.
Why is that? Come on. Is there a simple geometric argument why this is true? So we would like to have a one form. Oh, I mean, it's like you have a distribution, which is evolutive,
Yeah.
something like that.
Rotation is not equal to zero, then you can form. Was the probability, but it doesn't close with something like.
Yeah, right. But it's some, maybe you can use the Frobenius theorem to prove it. Yeah, because the tangent vectors form a hyper
No,
involutive distribution.
algebraically speaking, okay, it's like this. We can write it like this.
Well, if you know that the antisymmetric part vanishes, if you know that, and but Fran's suggestion seems a good one. I think that it really follows from the fact that this vector is orthogonal to a hypersurface, a really thing that forms a hypersurface all the way to integrability. Integrability. So that's probably why this is zero. Yeah, that sounds correct to me. But it is that's a tricky point, and I think important. Yeah. And then where did the Q dots come from?
The Q dot comes from the derivative. Very
Oh, wait,
time.
you wanted to.
Yeah, it's
Okay, so you replace the small n by big N and ddt. Right?
I replace the n with t minus the shift,
Right.
capital N, and then the derivative
Right.
T
So
is the
you
dot
can write
and
this as a Q dot.
is that
And
then
the derivative.
the time of the special part, yes.
Okay, good, fine. Yeah. Okay, then I see it approximately.
And then it's just because I made now this formula to it seems not so good, and actually at least you have the dot, so say the time derivative, and from that you get the conjugate variables and for all the stuff for the constraints and so on. That's why we have to start then from that and calculate the conjugate momentum with respect to Q gives to capital P, which is a combination of Q dot itself and other stuff. Okay, so I just wanted to write down the last part because from that we have to continue somehow. Okay, yeah, I think it's 3:45, so it's I don't like to do something like that.
So it's much better to do it slow and but do everything carefully.
Today I plan to maybe it was too hopeful to also introduce the SU2 variables. It's really impossible. And the point is that if I go slow, I think it will be very helpful. But at the same time, instead of 3 talks, it will be 10 talks.
So I think we're all spending time here, so it should be useful for everybody.
And it should be also only the introduction. This one.
That's exactly so. That means it should be understandable for everyone, right? The information should be there. If you don't do the calculation explicitly, at least you outline how it's done.
Okay. I'll go for it. Okay, thank you.
Thank you.
Pretty normal question, right? Everyone is going on for determinants? Yeah, block, yeah.
Chceš vidět tam ještě?
Jo, jsem tu, nebo?
Chceš ještě vidět formu, nebo mám to jít?
Já vím, jak to vypadá, takže v pohodě.
Dobře, tak jo. Tak vypadá.
Jo.